All right. Hello, everyone. Welcome to Lecture 13 in Aerospace 584 Guidance and Navigation. My name is Ankit Goyal, and today I will show you how you can convert a continuous time system into a discrete time system. Now, unfortunately, this is an online lecture, so I have zero feedback. So if I say something which doesn't make sense or isn't clear or possibly is erroneous, just email me and I will try to respond ASAP. And I'll also post these slides on Canvas. Okay, so let me start with the reason why we want to convert continuous time systems to discrete time systems. As you must have seen in your high school and undergraduate classes, most models of real-world systems are expressed in the form of differential equations. For example, this second-order differential equation describes the motion of rigid bodies. So if you're modeling the motion of a spacecraft, this is the equation you're going to be solving. The second equation here is a PDE. Let me get my pointers working. The second equation here is the PDE and is often used to describe diffusion processes. Now, as you know, most ODEs and PDEs rarely have a closed form solution. So the question is, how can we solve them? And we solve them by converting these differential equations into difference equations, which can be solved or which can be computed on a digital computer. Okay, so 78 years back, people developed these analog computers that could simulate the continuous time dynamics exactly. These analog computers basically had analog circuits which emulated integrators and differentiators. So you could use those elements to compute the terms of the differential equation. But you couldn't do much with these because these computers were very specific to the problem that was being solved. On the other hand, digital computers are very good at carrying out basic arithmetic operations. So complex functions can be constructed by a sequence of arithmetic operations. So you can compute a function, an expression like y equals f of x. X is your input, and you want to evaluate the value of the function f at the input x. So you can do this very easily on digital computers. Okay, so our objective today is to compute the solution of the differential equation x dot equals f of x and u. X is the state, u is the input, given an initial state x at some time t0. Now we can compute f of xu, but that gives us the rate of change of the state. That doesn't tell you where the state is going to be. So what we want to do is we want to construct a solution x hat, and I say a solution because we're not getting the exact solution of this differential equation. We are looking for an approximate solution of this differential equations. And once we have the approximate solution, we will compute that approximate solution x hat on a digital computer. So we will be focusing on step number 3 today, mostly in this lecture. So first, I will talk about sampling. Sampling is simply a process of obtaining discrete time signal from a continuous time signal. And I will talk about this phenomena, aliasing. This is what happens when you sample too slowly. Then we will discuss numerical integration, and I will talk about approximate solutions, stability of the approximated systems, the error introduced due to discretization, and we will see if we can reproduce the exact solution on a digital computer. Now, these topics are definitely by no means exhaustive, but these are just the things that we need to follow the main topics in this course. So let's look at sampling first. Sampling is simply a process of obtaining a discrete time signal from a continuous time signal. Let's suppose you have a continuous time signal. Y of t equals sine of t. So this is one harmonic. And I'm showing this one harmonic in the blue trace here. Now, if you look at the value of this continuous time signal, every t seconds, capital T seconds, and you record those values, you get a sequence. This sequence is called the discrete time signal, and it's denoted by y sub k. So y sub k, the value of y sub k at the kth instant is going to be sine kt, and this is the big T, not the continuous time t. The sampling period is the time between the two samples, and it's shown here. And the sampling frequency is the inverse of the sampling period. Finally, we call this index k, shown here in these pink dots. The index k is called the sampling step or just the step. And the dt signal, discrete time signal, y sub k, or discrete time signal at the kth step is y sub k. Okay, let's talk about aliasing. What is aliasing? Well, literally, alias is a name that a person assumes which is different from their true name. So the same person can have two names. Now let's look at this idea from the point of view of signals. Now let's suppose you had two signals. You had a signal X and you had a signal Y. Both of these signals are harmonics. And signal X has a frequency 0.1 hertz. Signal Y has a frequency 1.1 hertz. Let's suppose we sample these two signals at a time period of 1 second. And what you see is that both of these signals actually produce the same samples. And you can convince yourself that that is the case by looking at this bit of math. At the integer values of this index k, yk and xk, which are the samples of x and y, are exactly the same. So the point is that these samples, which are exactly the same, could have come from either the signal x or the signal y. So the frequency of the signal which is sampled is ambiguous, and this is what the result of aliasing is. So now I want to convince you that no matter what frequency, no matter at what frequency you sample the signal, you sample a continuous time signal, there are always going to be alias frequencies, and not just one. There are going to be infinitely many alias frequencies. Alias frequencies, again, are the frequencies that you cannot determine from your. Now, the aliased frequencies are all the frequencies that your DT signal could have come from that you just sampled. Anyways, it'll become clear. So let's suppose you have a sampling frequency f sub s steps per second, and you were to sample the signal x, which is one harmonic of signal of frequency f. You can check this math, and this basically is saying that at any step k, sine of 2 pi f kt, which is our signal x, is actually equal to sine 2 pi f plus big N times f sub s kt. Now, this is a different continuous time signal. This is a different frequency. But in the discrete time, or the sampled signal of these two frequencies is exactly the same. And this N is, again, an integer value. It could be -5, 4, 3, 2, 1, whatever. So there are a bunch of frequencies which produce exactly the same samples. So if we sample at f sub s steps per second, all the samples of these harmonics are going to be exactly the same. So if you recorded the samples, the frequency of the continuous time signal is ambiguous. What I'm saying is that f or f plus f sub s or f plus 2 f sub s could be the frequency of the signal that you just recorded. And these frequencies are called aliased frequencies. So how should we sample to avoid aliasing? Let's suppose you had three frequencies. You had frequency f1, frequency f2, and frequency f3 in your continuous time signal. And you sample this continuous time signal at frequency f of s, steps per second. So as we saw previously, looking at the samples, you couldn't say if the frequencies of the signal, the continuous time signal is f1 or f1 plus fs. These are possibly alias frequencies. So what if we sample at twice f sub s steps per second? Would that work? Actually, that also would not work, because whatever is the sampling frequencies, there are always going to be alias frequencies, and you can never be sure of the continuous time signal from which your samples came from. However, we can cheat a little bit. And if somehow you knew that the sampling frequency is actually larger than twice the largest frequency in your signal, then there is no ambiguity in the frequency of the sample signal. You can always reconstruct the correct signal if your sampling frequency is larger than twice the maximum frequency in your signal. You need the factor of 2 comes because the negative frequencies and the positive frequencies basically have the same effect. So anyways, this result is actually known as the Nyquist-Shannon sampling theorem, and it says that if the largest frequency in the signal is f, then it is uniquely captured by sampling at 2f frequencies. So the time period of your sampling should be less than 1 over 2f. What this is saying is that sampling frequency should be at least twice the largest frequency in the signal. Okay, so far we have seen how to sample a continuous time signal to get a discrete time signal. Now let's focus on the main problem of this lecture, which is converting a continuous time system to a discrete time system. So let's say we have an ordinary differential equation, which is a continuous time system. X star equals f of xu. Here, x is the state of the continuous time system. And we are going to assume that t is the sampling period, so that xk is the sample continuous. Oops, sorry. Let me get the laser pointer working. So t is the sampling period, and x sub k is the sample continuous time solution. Now, we don't actually have x sub k because we don't have the continuous time solution x of t. So if we don't have x, we don't have we don't have the sample continuous time solution. But we do have the input u, so we can sample it, and uk denotes the sample input. Now, our objective is to construct a difference equation shown here. And we want to construct this discrete time system such that the state of the discrete time system x hat k approximates the state of the continuous time system x of k. And like I said, x hat k is the state of the discrete time system, and in general, x hat k is not going to be x of the discrete time system state is not going to be equal to the continuous time system state. And our goal is to construct a DD system where we get as close to the CD continuous time system state as possible. Okay, let's look at some of the methods we can use to construct discrete time systems. So the first method is called the forward Euler method, and it takes a continuous time system dynamics here, and it approximates the x dot in this continuous time dynamics with this expression. And you can see that in this expression, the derivative x dot is being approximated by looking ahead, looking forward. X k plus 1 means that you're looking ahead at step k. So that's why it's called the forward Euler method. So once you use this approximation in this continuous time dynamics, we can write down the discrete time dynamics as this. So x hat is the state of the discrete time state, and x is the state of the continuous time state. Okay, let's look at an example now. Suppose we had a scalar ordinary differential equation x dot equals ax. This is a continuous time system, and we want to construct a discrete time system for this particular system. So we approximate the x dot using the forward Euler method, and doing some algebra, we can write this discrete time system. And now we want to check how close does this discrete time system get to the continuous time system. So to check that, we need to know what the true solution is. The true solution of x dot equals ax is, it's actually very easy to compute. X is given by exponential at times initial condition, and in all these 4 plots, in the blue trace shows the true curve. The red solution is the discrete time solution, discrete time system solution. And these 4 plots show the solution of x hat for 4 different values of the time step. And intuitively, you can see that as the time step t gets smaller and smaller, your discrete time solution is going to get closer and closer to the continuous time solution. So for t equals 0.1, we have a really good approximation, whereas for t equals 0.9, we have not a good enough solution. Okay, so let's look at a different method. The next method is called the backward Euler method. We start with the continuous time dynamics as before, but instead of approximating looking forward, we are going to approximate x dot looking backwards. So the x dot is approximated by xk minus 1 over this sampling period. And using this approximation, we can write the discrete time dynamics shown here. Now note that x hat k actually appears both on the left-hand side and the right-hand side. So we have to do a little bit more work in getting the right discrete time system using the backward Euler method. Again, let's look back. Let's look at the x dot equals ax case. We replace x dot with the backward approximation, and using some algebra, we find that this system is the discrete time equivalent or the discrete time approximation of x dot equals ax using the backward Euler method. Now this looks slightly different from the forward Euler approximation. In the forward Euler approximation, we had 1 plus TA times the state, whereas in the backward Euler, we have 1 minus TA inverse times the state. So again, let's look at how good the approximation is. I'm showing in blue the true solution. In red, I'm showing the forward Euler based discrete time system solution. And the green trace in all the 4 plots show the solution with the backward Euler approximation. And as you can see, the backward Euler approximation is actually slightly better than the forward Euler method. Okay, so far we have seen 2 methods to discretize a system, and we saw that the approximation approximation improves as the time step is reduced. However, the smallest time step that you can use depends on the hardware and the application. So if you're running on a small Arduino unit with 8 megabytes of memory and you need real-time estimates, you are limited in the smallest time steps you can tolerate. So the trade-off is between the accuracy of the solution that you want and the computational resources you have. So once you have a fixed hardware, that dictates the smallest step you can take. Okay, apart from accuracy, do we have to worry about anything else? And the answer is yes. We want to make sure that the discretized discrete time system is in fact stable. So let's review a little bit of stability theory here. In linear system, you must have seen that for the linear system, x dot equals ax plus pu, where lambda j is the jth eigenvalue of A, the linear system is asymptotically stable if and only if the real part of the real part of each eigenvalue is less than 0. So you can see this in a simple example. So x dot equals ax. In this system, the solution of this system is given by this expression, the initial condition times the exponential at. The eigenvalue of A in this case is just A, and we can see clearly that A less than 0 is the necessary and sufficient condition for the exponential at to actually go to 0. So corresponding results in discrete time systems are shown here. So if you have a discrete time system, xk plus 1 equals a sub d, xk plus b sub d uk, and lambda j is the jth eigenvalue of this matrix A sub d. The discrete time system is asymptotically stable if and only if the norm of each eigenvalue or the absolute value of each eigenvalue is less than 1. And again, we can see this from a simple example. Let's look at this discrete time system. The solution of this discrete time system is shown here. Again, eigenvalue of A is just A, and this expression, this term A to the K is 0 if and only if the absolute value of A is less than 1. Okay, now that we know what the stability in discrete time system looks like, let's analyze the stability of the discretized system that we obtain with the forward Euler method. We'll do this by analyzing a simple scalar linear case as always. So let's suppose A is less than 0. In that case, x star equals AX is asymptotically stable. And this is the discrete time system that we obtained using the forward Euler method. And the question we are asking is this system stable for all values of t? Okay, let's check. So the eigenvalue of 1 plus Ta is just 1 plus Ta. And if the discrete time system is stable, we want the eigenvalue to be between -1 and 1. Now, in this particular case, that is actually not true. And to see that, just let's just take A equals minus 2.5. And with a time step of 0.1, we compute that AD is equal to 0.75. Now 0.75 is less than 1, and hence the discrete time system is going to be stable. But if we set the time step to be 1, we actually see that the corresponding AD is going to be minus 1.5. And the discrete time system that we get here is actually unstable. So in the Euler method, the time step t needs to be small enough to make the discrete time system stable. Okay, similarly, we can do the same analysis for the backward Euler method. We assume that A is less than 0, which makes x star equals AX asymptotically stable. And the backward Euler approximation, the DD system obtained with the backward Euler method, is shown here. And the question again is this stable for all values of t? Okay, this is supposed to say t. I'll fix this in the slides. Okay, let's check. The eigenvalues of 1 minus Ta inverse is 1 minus Ta inverse. And for stability, we want this eigenvalue to be between -1 and 1. Now note that since A is negative, 1 minus Ta is always going to be a positive quantity because T is positive, minus of a negative number is positive, so this ends up being negative. Not only negative, this term is actually always greater than 1, which means that when I take the inverse of this, the inverse is always going to be less than 1. So the eigenvalue is always less than 1, and it's always positive. So the backward method with any time step t greater than 0 guarantees the discrete time approximation system stability. However, the problem is that the discrete time system that we obtain using the backward Euler method, it might be difficult to solve for x hat k. We might not be able to solve for x hat k. So even though we get unconditional stability, it might not be solvable, so might not be usable. Okay, next, let's talk about the errors in the discrete time system. So again, we consider the system x star equals f of xu, and let's suppose you had the solution x of t. Okay, so using Taylor expansion, we can find out that the solution x of t satisfies this equation. X of t plus the sampling time is given by this expression. And in this expression, I can replace x star because I know what x star is. X star is just f of xu. So we basically get this equation. Now, to look at the error, we want to characterize the error between the x hat, which is the state of the discrete time system, and x at kt, which is the state of the continuous time system. So we want to look at this error, and we want to see how it propagates. So let's say that the solution of the dt system is given by this equation, or the dt system is given by this. So we want to see how the error propagates. So we just calculate x hat k plus 1 minus the state at the next instant, and it is given by this expression. So now for both of the discretization schemes, we are going to look at what ends up on the right-hand side, and that will tell us how the errors propagate in these two methods. And what we are doing, basically, I'm trying to show it here pictorially. So we have the solution at the kth step. We have the true solution x, and we have the, okay, let me not say true solution. We have the state of the continuous time system at step k, and we have the state of the discrete time system x hat k. And both of these systems are allowed to evolve. The discontinuous time system goes from kt to k plus 1t according to the differential equation, and it lands here. And the discrete time system is simply making a jump from step k to k plus 1, and it lands here. So even if we start from the same state, there is going to be error between these two states. And this is the error that we are trying to characterize. Okay, so let's focus on the forward Euler method first. So this is the equation that we got in the last slide. And in the forward Euler method, the x hat k plus 1 is given by this expression. So once we replace this big F by this term here, we can write the error propagation as this equation. And let's suppose that at some instant, some time t equals kt, let's suppose that the state of the discrete time system and the state of the continuous system were exactly the same. So x hat k and x of t were same. So in that case, I can cancel this, these four guys out. X hat k is canceled by this, and t times f is canceled by t times f here. And all I'm left with is this equation. And what this is saying is that if you didn't have any error at step k, at k plus 1, your error is going to be proportional to t squared. Next, note that to go from time 0 to time t, we need to take a minimum of small t divided by big T number of steps. So the accumulated error at, okay, this is supposed to say t, the accumulated error at time t is going to be proportional to t, because at each step we have errors which are proportional to t squared, and we are supposed to take small t divided by big T number of steps. So the total error at time t is going to be proportional to your time step t. And this is the reason why we say that the forward Euler method is first order accurate. So you can do the same type of analysis, and we'll find that even for the backward Euler method, we only have first order accuracy. Okay, so these two methods that I spoke about so far, both of them are first order. One is conditionally stable and the other is unconditionally stable, but these are very basic methods. In most practical problems, we use much more advanced methods. In fact, a class of numerical integration method is called the Rankara methods that you must have seen many times. One of these is the famous RK4 method, and it is as simple as it is famous. We start with a continuous time system, and RK4 gives us a discrete time system which looks like this. So x hat k plus 1 is equal to x hat k plus 1/6 of this expression, where each of these coefficients, I'm sorry, k1 to k4 are given here. And the local truncation error in this particular scheme is proportional to t to the 5. And again, we take, I'm sorry, small t over big T number of steps to go from 0 to time t. So the accumulated error is going to be proportional to t to the 4. So we can apply the same stability and error analysis that we use with the forward Euler and the backward Euler method to study the stability and the error in the RK4 method. First, we need to explicitly construct the DD system for this continuous time system. So using the expressions of K1, K2, K3, and K4, and the fact that f of xu is simply ax, we can find that x hat k plus 1 is actually equal to this big expression times x hat. And if you look at this expression long enough, you're going to see that this expression actually has the first five terms of the exponential at. So RK4 is doing a much better job of approximating the true solution. In fact, the forward Euler only was approximating the solution with the first two terms, whereas the RK4 is approximating the true solution with first five terms. And this is the reason why this is also fourth order accurate, because this expression is a fourth order approximation of exponential AT. Anyways, let's test all these methods now. We have the forward Euler method, we have the backward Euler method, and we have the RK4. Let's try to solve this continuous time system. Again, we can solve this continuous time system analytically, and the analytical solution, which is the true solution, is shown here in the blue trace. The discrete time solution of the three approximate I'm sorry, the three approximating techniques are shown here in red, pink, and green. The green is the RK4 method, the red is the forward Euler, and the pink is the backward Euler. And as you can see, for both time steps t equals 1 and t equals 0.5, the RK4 method is much closer to the true solution, much more closer to the true solution than the other two schemes. So in other words, for the same time step t, the error in RK4 is less than the error in the backward Euler, and is also less than the forward Euler scheme. But you have to note that the RK4 actually evaluates the function, this right-hand side, 4 times per step in comparison to just 1 time, as it is done in the forward Euler and the backward Euler case. And this is not the end of it. There are actually a lot of methods to numerical integration. There are way too many to be covered in one lecture. And here is a small list of the Rankara methods available on Wikipedia. You may want to check it out. Okay, so far we have seen that we can use some tricks to find an approximate solution, or we can construct a discrete time system which approximates the continuous time system. Now the question is, can you construct a discrete time system whose solution exactly matches the continuous time system? And the answer is yes. Let me show you how by looking at a simple example. So we have seen the system many times now, x dot equals ax. This is very easy to solve. The solution is shown here. X of t is just given by exponential, this exponential times initial condition. And I can rewrite this solution as this. So x of t plus big T is given by exponential a big T times the state at time t. Now looking at this solution, let's construct a discrete time system, and the discrete time system is given by this. We just consider this discrete time system. Now let's suppose that x hat at 0 was exactly equal to x of 0. So the initial condition of the discrete time system, x hat 0, and the initial condition of the continuous time system, x of 0. Let's just assume that they were 0. Then for all times which are equal to kt, the discrete time state is going to reproduce the continuous time state exactly. So why does this happen? Well, it happens because this discrete time system was constructed using the exact solution. That's why the state of the discrete time system is exactly equal to the continuous time system. And this is a method which we can use to construct DT systems so that the solutions are exact. Okay, so what about other DT solution? What about other techniques that we have seen so far? We have seen the backward Euler, the forward Euler, the backward Euler, and the RK4. And I just showed you an exact technique which gets us the true solution. So when we use the exact solution, obviously we are going to get the exact solution. When we use the forward Euler, we actually capture the first 2 terms of the true solution. And when we use the backward Euler, 1 minus AT inverse, you can actually expand 1 minus AT as this term, and then we can see that 1 minus AT inverse also captures the first 2 terms of the true solution, and RK4 captures the first 5 terms. So RK4 is the most accurate backward and forward are first order accurate, but exact is just the exact. Exact is the best solution that you can get. Okay, now let's focus on the system that we are going to be using a lot in this course. An LTI system, x star equals ax plus bu. Here, x is a vector, not just a scalar. Now, it turns out that we can actually solve x star equals ax plus bu exactly, and the exact solution is given by this equation. And to convince yourself that this equation, this solution is the true solution of this system, you can differentiate this system and see if we get the right-hand side. To differentiate this expression, this includes an integral. So we would need to use the Leibniz formula, which is shown here. So using this Leibniz formula, you can, again, pause me and look at this equation for a while, and then you will find that x dot of t, which is the derivative of this expression, ends up being equal to ax plus bu. Okay, so we need one more trick to construct a DT system, to construct an exact discrete time system for a continuous time LTI system. We need what we call as the zero order hold. A zero order hold basically converts a discrete time signal, y of k, to a continuous time signal. So it's the opposite of sampling. So sampling was converting a continuous time signal into a discrete time signal. A zero order hold converts a discrete time signal to a continuous time signal. And it does that by simply holding the sample at its value for the entire sample period. So now that zero order hold is going to produce a discontinuous signal. So let's look at an example. Let's look at this figure. We start with the continuous signal. Continuous signal is shown here in blue. We sample the continuous signal. When we sample the continuous signal, we get these red dots. And then if we hold these red dots for the entire sampling period in this case is 0.1 seconds, I think. So if we hold this value for 0.1 second, and this value, and then this value, and this value, this gives us the discontinuous or the reconstructed signal. This signal is the output of the zero order hold. So we need this to compute the exact solution. We need this to construct the discrete time system, which is going to give us the exact solution of the continuous time system. Let's look at how we can construct a DT system which provides us the exact solution of the continuous time system. So we saw in the previous slide that the solution of the continuous time system is given by this blue equation. And we want to construct a discrete time system x hat k plus 1 equals ad x hat k plus bd uk, such that the state of the discrete time system equals the state of the continuous time system at each sampling instant. Okay, so let's look at this exact solution and let t naught be equal to kt and t be equal to k plus 1t. So we are basically looking at how the continuous time system goes from one step to the next step. Next, we are going to assume that we have a very special input. The input u is constant between the samples. So that is for all the times tau, which are between the samples kt and k plus 1t, the input is held constant, or it's like the zero order hold equivalent of the sample input uk. So if we use this input in this integral, we can actually take this u of tau out, because u of tau for all tau between the limits of the integration is constant. So we can take this b u tau out, and u tau, we can replace this with uk. So, okay, let's start with each term. The first term, e to the a t minus t naught, if we substitute t and t naught into this equation, we get a t. So we have e to the at xk. And the second term, which is the integral, looks like this. We can take the b u tau out. It becomes b uk. And if we replace tau minus kt with sigma, we can see that this integral actually reduces to this, this term here. Now note that this integral and this term does not depend on k. So we can define a sub d as this and b sub d as this, and that will give us the discrete time system that we are looking for. So in the special case where the input ut is constant between the samples, the discrete time system given by this equation, where AD is equal to the exponential AT and BD is equal to this term, provides the exact solution of the continuous time system, x dot equals ax plus bu at the sampling instant. Now, I have to warn you that this discretization is based on the exact solution in a very special case. U of t in general is not going to be constant between the samples. So the discrete time solution x hat k is not going to be equal to the sample continuous time solution. They are equal only in the special case where the input ut for for the continuous time system is constant between the samples. However, if we reduce the time step t, the error between the discrete time system solution and the continuous time system solution can be reduced. And this is very intuitive. This is the same stuff we saw with the other approximating schemes. So let's again look at an example. In this case, we are going to look at this continuous time system, x dot equals minus x plus cosine of t. So in this case, a is -1 and b equals 1. The input is cosine t. Now note that this cosine t is actually not constant between any two samples, because whatever sample time you choose, this input ut is always changing. Anyways, with this value of a and b, we can construct the discrete time system AD and BD. So AD is simply given by e to the minus t, and BD can be computed by this integral, which ends up being 1 minus e to the minus t. The input to the discrete time system is the sample input, uk, which is equal to cosine kt. And again, the input to the continuous time system is not constant between the sampling instants, but the input to the discrete time system is assumed to be constant. So anyways, we have the discrete time system looking like this. We have a continuous time system looking like this. And this continuous time system can actually be solved exactly. And the exact solution of the continuous time system is shown here. So we have the discrete time solution coming up from this equation and the continuous time solution coming from this equation. And we can look at these solutions for some values of t. So let's start with t equals 0.1. We start with the initial condition x of 0 equals 1 for both the discrete time system and continuous time system. And you see that the discrete time system, the continuous time system is shown here by the blue trace. It's the exact solution that I showed you in the previous slide. And the red solution, the red dots show the discrete time solution that we obtained with the discrete time system. And you can clearly see that there is an error between the continuous time system and the discrete time system. And this error exists even when we use the exact discretization, exact solution-based discretization. And this error is there because we are not, the inputs are not constant between the samples. So as I mentioned previously, when you reduce the time step, in this case, we have t equals 0.01. In the previous case, we had time equals t equals 0.1. The accuracy of the solution immediately improves. The error decreases a lot, but still the error is going to be erroneous. The error is going to be non-zero. So as you keep reducing the time step t, your discrete time system solution is going to get closer and closer to the continuous time solution. Okay, so in this plot, I'm showing the error between the discrete time system solution and the continuous time system solution for various values of t. So I computed it for 10 to the minus 8, 10 to the minus 7, all the way to 10 to all the way to t equals 0.1. And this blue trace shows this error metric. It's basically the error computed, error averaged over, not average, error, the error squared summed over all the time step. And we can see that as the time step increases, the error increases. But as the time step increases, the time to compute the solution also decreases. So if you use a small time step, the time to compute the solution is going to actually increase a lot. Note that the scales are different. This is a log scale and this is a linear scale. So for 10 to the minus 8, we have to wait, 11 seconds for the solution to come out. And for larger time step, we can get the solution in a very small fraction of the time. This little increase at the end is because of the memory allocation. This is a separate issue. We don't want to go into that. Anyways, so the point is, as the time step goes up, the accuracy goes down, and the computation time also goes down. Okay, to summarize, in this lecture, we saw that the signals can be easily discretized by sampling. The digital representation of sample signal introduces error due to quantization. Now, I didn't go into quantization, but I'm sure you have seen this from Professor Bernstein's earlier lectures. With the exact solution of ODE, the exact discretization of the system can be obtained, but even the exact discretization is erroneous. Now, I showed you multiple approximating schemes and, of course, the exact discretization. And there are errors in these solutions because of zero order hold of the input signal and the quantization of the variables. Okay, that brings us to the end of this lecture. It went worse than I thought it would because I have zero feedback. But anyways, if you guys have any questions, if you think I made a mistake somewhere in the slides or something is not clear, just shoot me an email and I will try to get back to you as soon as possible. Thank you so much.